or whether to use the traditional interpreted T-SQL access for accessing your memory optimized tables. And finally, in-memory OLTP was built with a large degree of concurrency in mind. And so when you think about concurrency, you think about concurrently running transactions in the system. Now, to facilitate and to be able to sustain a high level of concurrency in the system, we have a number of assumptions underlying the transactions on memory optimized tables that are a bit different from traditional disk-based tables. So I will go through some of the implications that this has on your application. So first off, memory optimized tables and indexes. Now this slide here, this shows you the DDL for creating a memory optimized table. And this should look all pretty familiar. I mean, it is a T-SQL language after all. You have your basic create table statement, you have your columns and your data types, but there are a couple of things that are new here. So first off, we have the keyword memory optimized here. So this is an indication that this table is indeed a memory optimized table. The second option that we've added is this option durability. So in this case, I selected durability is schema and data, indicating that the data in the table is fully durable. So it will survive any server crash, any operations on the table are fully logged, and a persistent copy of the table is kept on disk for recovery purposes. But for memory optimized tables, you can also choose to use a non-durable table. You would say durability equals schema only, which means that on server restart, the data is not retained, but only the schema is retained. The fact that it's non-durable will give you some benefits, including that you will never need to go to disk and operational table are not logged. That also, of course, means it is only suitable for transient data like session state and whatnot. Then we have a new type of index that we introduce specifically for memory optimized tables. And this is the hash index. Now a hash index is quite different from traditional clustered and non-clustered indexes. It is, instead of a B tree, the index structure is a hash table, which means that it is very efficient for point lookups. But you cannot do things like ordered scans or scans of ranges. I will go through that in a bit more detail later on. Another thing to keep in mind with hash indexes is that they are static. So when you create them with a certain size. This never changes during their lifetime. And also you need to specify actually how big it is going to be. You specify that through the bucket count. Now the fact that it doesn't change during its lifetime has some benefits, including especially performance benefits. But you do need to be aware that you need to specify this bucket count. And usually we recommend using between 1 and 2 times the number of unique index key values as the bucket count. But it is usually not a problem if you oversize it. So if it is like 10 times the number of unique index keys or 10 times the number of rows, that is usually not a problem. Then the second thing you may see here is that we have this index specification inline. So we added the capability to specify indexes within the create table statement. And in fact, with memory optimized tables, you are required to specify the indexes when you create the table, because the index data structures are tightly coupled to the actual table data. And you'll see here the second type of index we support for memory optimized tables, which is basic non-clustered index. This is very similar to traditional clustered and non-clustered indexes. The index itself has a tree structure, and the rows are in order in the index, meaning you can do order scans and you can scan ranges of the data. But it is different in the sense that it uses a different page format. It's latch free, so there's nothing like page latches or locks in there. And then besides a memory optimized table, we also introduced memory optimized table types. So this is very similar to an actual table specification. Similarly, you specify memory optimized on, and you have your index specifications in line. But now that you have a memory optimized table type, you can create memory optimized table variables actually throughout your application. You can actually use memory optimized table variables even without using memory optimized tables. And in some cases, this can give you some benefits, including relieving temp-DB contention, because memory optimized table variables, they don't live in temp-DB. They live in the user database, live in the memory space of the user database. And they will never flash to disk in any way, shape, or form. Now, let's talk about what happens when you create a table type or a table in general. So what happens behind the scenes is you issue or create table DDL, and behind the scenes we go through a process of code generation and compilation, and we take the table metadata and table access methods, and we generate C code, and we compile that to an actual DLL, and then we load this DLL in memory. Now you may wonder, hey, why do I need a DLL for tables? Well, that is because we want to optimize the table access methods as much as possible. We don't, at runtime, we don't want to start looking at metadata, starting to interpret it like, hey, there is the third column is of type integer, the fourth column is of type nvarchar40, so I need to dereference the pointers in this way. No, we bake that logic into the DLL for very efficient access to the table data. So that's the table. Then the indexes. There are a couple of properties of memory optimized indexes that I would like to call out here. So first off, memory optimized indexes exist only in memory. They are actually built on database startup. So any operations in indexes are not logged, and there's no copy of the indexes on disk. Right? There's a copy of the data rows on disk, but not of the indexes. And the indexes themselves, they also don't actually contain any data rows. If you know your classical clustered or non-clustered indexes, they contain data rows or parts of data rows with then potential pointers to the clustered index, which has the data rows. Instead, memory optimized indexes, they don't have any of the data, but instead they contain memory pointers to the actual data rows. So if in memory you have this data structure for the table, which has a bunch of rows, they are all byte addressable using 8-byte memory pointers, and the index just contains pointers to these data rows. And so there's also no such thing as a clustered index for a memory optimized table. That concept just does not apply here. Also important to keep in mind is that we don't have any duplication of data because every row exists just in one place. There's no duplication across the indexes. And the fact that you have these pointers to the rows from the indexes also means that all indexes are covering. So you never need to worry about included columns in indexes or in bookmark lookups or anything like that. No, every index is simply covering. And now we have these two types of indexes, non-clustered indexes and the hashed indexes. And a couple of things to keep in mind when deciding what to use the one or the other. So in fact, what we usually say is use the non-clustered index as a kind of baseline because the operations supported by a non-clustered index are very similar to the operations supported by classical B-tree indexes on disk-based tables, and then use hash indexes to further optimize point lookups. So let's contrast these points here. So with a non-clustered index, you don't need to specify any option when you create it. In fact, there's no option you can't specify. It is simply self-maintaining index that is dynamic, so it grows and shrinks with the size of the data. And with the hash index, you do need to specify the bucket count when you actually create the index. Then a non-clustered index is optimized for range lookups and order scans. So the data in a non-clustered index is in order of the index key, which means that you can scan the rows in order, and also you can scan just a range of rows. Let's say if you have an index on date, you can have everything between February 1st and March 14th, for example. That would be a range lookup. Hash indexes, they are specifically optimized for point lookups. And in fact, they cannot be used for things like range lookups or order scans. Then non-clustered indexes, because they are ordered, you can also just search on the leading column of the index key. If you have, let's say, 2 columns, say sales order ID, sales order detail ID, you can just search on the sales order ID and forget about sales order detail ID. On a hash index, because the hash value is computed based on the entire index column, you cannot search on just part of that index key. So you cannot search on a leading index key column. You always need to search on the entire index key. So with these 2 indexes, there are a number of considerations to keep in mind when you choose the type of index you want to use. So we usually say non-clustered is a safe baseline because it supports all the operations, including point lookups. And you want to use hash to specifically optimize inserts and point lookup operations. So an insert into a non-clustered index, there's also a penalty there because you need to find the right place in the tree to put the new row. Of course, with hash, always keep in mind inequality seeks, ordered scans not supported. Also, one thing to keep in mind is that you can have both types of indexes on exactly the same column. So if you have some column or some set of columns where you need to perform both a lot of point lookups and you need to perform range scans or ordered scans as well, you can have both the hash index and a non-clustered index on the same columns. Now, for the hash index, you have this bucket count that you need to specify. So you need to choose at least as many buckets as you have unique index key values, but oversizing is usually okay. So as I mentioned, if you have like 10 or 20 times as many buckets as you have unique index key values, that's usually still okay. And actually, it does not affect the performance of point lookups if you have too many buckets. If you have too few buckets, point lookups and insert performance will really suffer. So the bucket count automatically runs up to the next power of 2, and as a general recommendation, if you have a lot of duplicates in your index, we recommend usually to use a non-clustered index because it deals with duplicates a little bit better. And then also always keep in mind with hash index does not support seek on a subset of key columns. I know I keep repeating this point, but we've seen actually a lot of customers run into this issue. So you must always seek on exactly the columns. Sorry, the index key must include exactly the columns you are seeking on. So it must include exactly the columns that you have in the where clause or subset thereof. Okay, so now let's switch to a little demo. So what I'm going to do here is I'm going to create a database, create a memory optimized table, and look at some of these index properties. So I'm going to create my database. Then I'm going to add this new memory optimized data file group, add a container to the file group to enable it for in-memory OLTP. I need to do that to be able to create memory optimized tables. Then I set the database option memory optimized elevate to snapshot to on to automatically map read committed to snapshot. So I can just use my read committed isolation level in the syntax, and I automatically access the memory optimized tables using snapshot isolation. a little bit more about that later on. Now let me use my database, and now I'm going to create a table. So I'm going to create this table sales orders, which has these 3 columns: order ID, order date, order status, and it has a non-clustered index on order date, because I may want to do range searches on dates, and it has a hash index on order ID, because in this case I probably want to do only point lookups on the ID column. And this next square shows that we have integrated these new features in the system catalogs and the catalog views. So here you can see that my new table is indeed memory optimized, and it has a default durability, which is schema and data. So let me go ahead and insert some sample data. I'm going to insert 5 sample sales orders, which have some order dates, which are in different order. Afterwards, I'm updating the stats, because we don't support auto-update stats. We support auto-create, but not auto-update, so you will need to do that. So what I'm going to do now is, first I'm going to do point lookup using hash index. So I'm going to search for the row with order ID 2. Okay, and it returns. Now let's have a look at the query plan. So we see here there's an index seek, and a couple of things I want to call out here. So it's an index seek on a non-clustered hash index. That is the hash index I'm using. Storage memory optimized, so this is how you know that it is on a memory optimized table. And we can see here the actual seek predicate on the equality seek on order ID. Okay, so that worked fine. So let me now attempt to look at a range. So I'm going to look at all the rows with order ID greater than 2, which is essentially a range of orders. And the query, of course, can be satisfied, but let's have a look at the plan. See what actually happens under the hood here. So what we can see here is that, in fact, there is no index seek when inequality predicate. Instead, we have an index scan on the hash index, and we have a filter. If we look at more detail, we see that the filter is on an inequality predicate. And yeah, I have this hash index on order ID, which means I can actually not do any inequality lookups, only equality. Now, similar for sort order, I'm now going to order by order ID. Again, the query works as expected, but when we look at the actual query plan, see here what we can see is we have an index scan followed by a sort, and we see the sort was ordering by order ID. So we have this very expensive sort operator because we could not use the hash index, because a hash index is not sorted. Okay. So then let's look at the capability of a non-clustered index that we have on order date. So first I'm going to do point lookup on order date. So looking at one row with an order date, the row is returned. When I look at the query plan, so here we can see that we have an index seek, and we have an equality predicate. So equality searches are supported for non-clustered indexes. And let's look at the range. So, and I'm going to look at all the orders greater than January 1st, 2013. Query works. Let's have a look at what show plan says. Now we see here indeed we have an index seek operator. We don't have a filter anymore. And looking at the seek predicate, we can see that this was indeed an inequality seek. So if you need to do any of these type of operations, inequality seeks, or you need sort order from the index, use a non-clustered index. Yeah, okay. So I have here actually the example of the sort order. I'm going to order by order date. And we see in this case, indeed, we just have an index scan of this non-clustered index, and we don't need a specific sort operator to fulfill the sorting requirements in this case. Okay, let me clean up and go back to the deck. So then we have our memory optimized tables and indexes. And now the question is how to access those. So first we have these new natively compiled stored procedures. And this slide shows you the syntax for creating such a procedure. It is the SQL stored procedure, but there are a couple of options that are required when you're using a natively compiled stored procedure. But the T-SQL content, the queries are just your typical T-SQL. So the first option is native compilation to indicate that this is indeed a natively compiled stored procedure. Then natively compiled stored procedures are required to be schema bound. So you must use schema binding because we cannot have our tables disappearing from underneath us when we compile the DLL. So the table and the procedure DLLs are very tightly coupled. And then also you're required to specify execution context, and executors color is not supported. That's because we don't want to do permissions checks on each execution. So we only do our permissions checks when we create the procedure or when permissions in the system have changed. So typical executions of natively compiled stored procedures, we don't need to check any permissions because we already know under which user the procedure is going to execute. And then we have this nifty new construct called an atomic block. Well, it is new for T-SQL. It is an ANSI standard, so it's part of the ANSI SQL standard. And what it gives you is atomic execution. So either everything in the atomic block succeeds and commits, or everything fails. So practically, if you don't yet have a transaction, it will give you a new transaction and it will commit at the end, or otherwise it will create a save point when you begin atomic. And if there is any, and if you throw out of the atomic block, you roll back to the save points. And we do support things like try catch within the atomic block, so you can always cache error messages to prevent throwing out of it. And then we also want to fix the session settings at create time to ensure that we don't need to interpret any specific state, and also to ensure that every execution of an atomic block is always the same, always has the same results. Now there are two settings you are required to specify: the transaction isolation level and the language. Language is mostly related to date format in this case, and there are some other session settings where we pick a default for you. Like, for example, ANSI nulls is always on in atomic blocks, because frankly ANSI nulls off does not make any sense. Now if we look at what happens under the hood when you create a stored procedure, it looks very similar to creating a table. Also we do some code generation, we create a DLL which we then load. The one important thing here to keep in mind is that we actually do the query optimization at compile time. So we create the query plan when the procedure is created, and the query plan is then baked into the DLL. And this is in contrast to traditional stored procedures where the query plan is created on first execution of the procedure. Now I want to kind of contrast the two methods of accessing memory optimized tables. So we have the natively compiled stored procedures, which are these new type of stored procedures I just talked about. But we also have what we refer to as interpreted T-SQL access, which means using just any old T-SQL ad hoc batch or any SQL module, even a traditional stored procedure to access memory optimized tables. In fact, you can access memory optimized tables in every context. You can also access a disk-based table, except for cross database. That's not yet supported. So if we contrast these two ways of accessing them, so natively compiled stored procedures, they have some limitations, but we created them for maximum performance. So if you really want to push the maximum performance out of your application, you'll probably want to use natively compiled stored procedures. But they can access only memory optimized tables, and in SQL 2014 we have quite a few restrictions on the SQL you can use inside them. But you can do basic insert, update, delete, and selects with where clause, and also you can do inner joins, as well as group by aggregation. But there are quite a few constructs you cannot use, including OR, union, and subqueries. Now, if you use interpret SQL access, you can access both memory optimized and disk-based tables in the same transaction, or even in the same query. You can just do the joins across. For example, if you have reference tables. Of course, it's less performant, but you have virtually the full SQL surface area. So you can go crazy with your window aggregates, with your subqueries, case, all these things. You can just use those. So you'll want to use natively compiled stored procedures specifically for your OLTP style operations that are really in performance critical part of your application. Interpreted SQL access, you'll want to use this for things like ad hoc queries and also reporting style queries. And when the query service area you need is not available in native procs. Okay, so let's switch now to the next demo, which is about accessing these tables. So what I want to do here is I want to contrast interpreted SQL access and a very simplistic form of a natively compiled stored procedure. Now what I'm going to do is I'm going to insert 1,000,000 rows into my memory optimized table. I'm first doing it using an ad hoc batch. So this is using interpreted SQL access. And for these 1,000,000 rows, you can see this took about 7 seconds. Okay, and we can verify that these rows, we have indeed data in a table. Because it's a hash index on order ID, the order ID does not appear in any particular order. I'd remember the about 7 seconds that it took to insert these 1,000,000 rows. So what I'm going to do now is I'm going to create a natively compiled stored procedure. And this natively compiled stored procedure has the exact same logic. It also inserts 1,000,000 rows. It does not need to begin tran and commit because it has to begin atomic and end, which ensure that it runs in a single transaction and commits. So let's see how long this takes. So in this case, this took a bit under 2 seconds. The elapsed time, CPU time is even less. Now, the reason why this is so much faster than doing this in interpreted SQL is that it was all compiled down to native code. So the loop that's in here became a very tight loop in C, which can be executed very efficiently. And we use the VC compiler optimization. So essentially, we're doing a lot of work inside this one natively compiled stored procedure, which means the whole operation is going to be a lot faster than when just doing interpreted SQL. And we can see the data is indeed there. No, but let's delete the rows. Now, whether you get benefit from actually using a natively compiled stored procedure, that often depends on how much work you actually do in it. In this case, we were doing a lot of inserts with a lot of rows inside the procedure, and this gave us a lot of benefit. Now, the question is, do I get this benefit if I just touch one row inside my natively compiled stored procedure? So this procedure inserts just a single row in my sales orders table. You can see here it's like a singleton insert statement. What I'm going to do now is I'm going to again insert 1,000,000 rows within this one transaction, but now each insert translates to a call this natively compiled stored procedure that inserts just two. And you can see this goes a bit slower than when doing all the 1,000,000 inserts in one execution. In fact, when we're now looking at the time it took. Oh, got to get my zoom in to work. This took about 12 seconds. So this is in fact even a little bit slower than when just using interpreted T-SQL ad hoc inserts. That's because SQL Server always has a bit of overhead for calling a stored procedure. Therefore, so the point here is that with natively compiled stored procedures, just by using them doesn't mean you get benefits. It is usually if you have a bit more complicated operations where you touch several rows that it will work faster. And also in general, we would recommend to call the natively compiled stored procedures directly from the client using prepared execution. That is the fastest way to execute these procedures. Okay. So let's get back to the deck. So the next thing I want to touch on are the transactions on memory optimized tables. So why this is important is because we have this new concurrency control mechanism within memory OLTP that removes all latch and lock contention. So because we want to sustain a very high level of concurrency, we want to scale linearly in the number of cores in the work that you're doing. So therefore, we remove latches and locks, and this does have some implications on your application. So when talking about concurrency control with in-memory OLTP, there are two key things I want to emphasize here. So first, it's actually a multi-version system. So the data itself is multi-versioned. The table data structures contain multiple versions of the row. It's not stored in TempDB or anything like with traditional snapshot isolation on disk-based tables. No, it is part of the data structure itself that is in memory. And having multiple versions means that you can have one transaction writing to a row and another transaction reading that row at the same time. The other transaction will just read the previous version of the row. And hand in hand with the multi-versioning comes snapshot-based transaction isolation. So all transaction isolation levels with in-memory OLTP are snapshot-based. You do your reads always as of the begin time of the transaction, and we use this multi-versioning as the mechanism to implement snapshot-based transaction isolation. So also higher isolation levels like serializable, they use snapshot for their reads. And again, no TempDB usage. All the row versions are part of the basic table data structure. Then the concurrency control is optimistic. So we assume there are no conflicts between concurrent transactions. We assume that two writers are not going to write to the same row at the same time. And we see that in most applications, it is indeed very unlikely that you have two transactions that want to update the same row. Like, for example, you often have this example of account balance, right, where you want to have good isolation between your transactions. But it is not very often that you don't deposit two amounts of money at exactly the same time to your bank account. Right? That is it can happen, but it's very uncommon. So we are saying, okay, we assume that this is just not going to happen, and we don't take any locks, we don't take any latches, so we have no blocking in the system, and this also allows to minimize the context switches. So context switch is when you have a thread executing on a core, and you change the context to start execution of another thread on the core. And we have seen that a single context switch can be more expensive than the entire execution of an OLTP style transaction. So for these rare cases where you do have conflicts between concurrent transactions, let's say someone does try to deposit two amounts to the same bank account at the same time, We detect conflicts when they occur. So if you have these two writers trying to update the same account balance, let's say one of them, there is a conflict detected in the system and one of them will fail and will need to retry the transaction. Similarly, for repeatable read and serializable isolation, we optimistically assume that this isolation holds, and at the end of the transaction we verify that this indeed can indeed be guaranteed. If not, you need to retry the transaction. Also, one thing to keep in mind here is that we have no deadlocks, right? Why not? Because we don't have locks. It is plain and simple. So that is something you don't need to worry about when you have memory optimized tables. So when then talking about support isolation levels. So our basic isolation level is snapshot. So all reads are consistent as the start of the transaction, which is a much stronger guarantee than read committed gives you. Read committed only says all the rows you read have indeed been committed to the database. Now this is much stronger. We're saying all the reads are consistent as of the start of the transaction. So you see a consistent snapshot of the database. It existed at the start of your transaction, and every subsequent read within the same transaction will return exactly the same rows. Now writes are of course always consistent, and we do this conflict detection to ensure that no inconsistencies can occur. And we recommend using this database option memory optimized elevate to snapshot to map read committed, which is the default isolation level in SQL Server, to map it automatically to snapshot when you access memory optimized tables, so you can minimize the application changes you need for incorporating memory optimized tables. And we have seen that in many applications this just works. Just using snapshot instead of read committed just works. Now, it doesn't mean that it always works, because there are some applications that depend on some of the quirks of the read committed isolation level, like that you see updated versions of the database with each subsequent statement in a transaction, and also the fact that you have this locking behavior. But in most cases we've seen that using this just works. But of course, always test. Then repeatable read, next isolation level. You will see in MSDN that for disk-based tables, this is, I think it's defined in terms of logs that are taken. But of course, logs are just an implementation mechanism. You're interested in the guarantee you get from repeatable read. Repeatable read just means that read operations yield the same row versions if you repeat them at commit time. So the rows that you are reading have not changed in the database between the time you read them and the time you commit. So with account balance, for example, your account balance is not up if you read at some point in a transaction. It's not updated before you commit. And with serializable, in addition, it guarantees that there are no phantom rows. So if you perform any scan a second time at commit time, there are no additional rows that you would have missed. Why it's called serializable is because transactions are executed as if there are no concurrent transactions. So if you take every committed serializable transaction, you can create one serial path of executions. Now for repeatable read and serializable, we realize that these can be violated. Right? So if you can read some row and some other transaction can update it and commit before you commit. Similarly with serializable, someone can insert a row into a range that you just scanned. So what we do then is at the end, when you want to commit your transaction, we check whether any of these situations occurred, and if so, we fail commit at that time, and then the client will need to retry. So here I have a simple example of typical write conflict. So we have here transactions 1 and 2, both using snapshot isolation. It doesn't really matter when these transactions begin. It matters which transaction updates the row first. So we have this row 1, 2, 3, which is updated first by transaction 2 at time 3, and then transaction 1 comes in at time 4, attempts to update this row, and it will fail at this time. The transaction will need to be retried. So what happens here is the first writer always wins. So guidelines for using this new transaction model. So first we recommend to typically use this new database option, memory optimized elevate to snapshot, to make migration easier. Then we don't support any logging hints like update log or xlog or whatever. So instead, you should declare the isolation level that you want to use. If you're using an xlog hint now, you probably want to have serializable isolation. And then use retry logic to handle conflicts and validation failures, either in the client application or using a wrapper stored procedure. And also, you will want to avoid long-running transactions. Long-running transactions are, in general, bad in database systems because they keep consuming resources. But with memory-optimized tables, they're particularly bad for two reasons. One is that they hold up garbage collection of old row versions, because we always need to keep the row versions around in memory that are still needed by the oldest running transaction. So if you have a very long running transaction, you hold up garbage collection of a lot of rows, and this can mean you run out of memory. Also, if you have a very long running transaction, there's more chance of conflicts happening, so more chance that you will do a lot of work for nothing and you will need to retry the transaction anyway. Okay, so now I have a demo for the transactions. So let's make sure the cleanup is done. So what I'm going to do here is I'm going to contrast the behavior with traditional disk-based tables and using the default read-committed isolation level with the behavior of snapshot isolation on memory-optimized tables, where we have this optimistic multi-version concurrency control mechanism. So I'm going to use the same sales orders memory-optimized table I had before. What I have now is I also created a disk-based table with the same indexes and the same schema, the same columns, and I see I have syntax error here. Let me quickly fix that. Apologies. So what I'm now going to two rows with the disk-based table and the memory-optimized table. So let me make sure that I'm connected to the same database on my second connection. So what I'm going to do, my first connection, I'm going to start a transaction and I'm going to update order 1. Now what happens is, because it is a disk-based table, I take a lock on this particular row, because I made this change in place, but my change has not yet been committed, so nobody is yet allowed to read it because its transaction is not committed. So in my second connection, if I attempt to read the same row, you can see that the query is now executing. Actually, it is blocking on this lock. So it's waiting for this lock to be released to actually read this row and return to the client. So if I now go ahead and commit my transaction, commit succeeds, and you can see that, in fact, the row is now returned with my updated order status too. So let's see what happens with snapshot isolation on memory-optimized tables. So I have here the same statement for memory-optimized table. So again, I'm going to start a transaction, going to update my row 1, and now let me select this same row. Now in fact, the query returns immediately because there was no lock to block on or anything. And in fact, I'm just reading an older version of that same row, reading now with order status 1. So what happened when I ran this particular update statement, before it created a new version of the row, but that new version is not yet committed, so it's not yet visible, it's not yet returned to a client. So instead the older version is returned. But now if I attempt, now remember the transaction is still running, so it has not yet committed. So now on my second connection, I'm going to attempt to update this same row 1. What happens now is that there is this write conflict that happened because I'm attempting to update a row that was already previously updated, but not yet committed, right? So therefore it needs to fail, otherwise you have two versions of this row floating around. We cannot have that. So as you can see, the transaction attempted to update a record that has already been updated. But now so in fact, usually what you need to do in your client application is retry this transaction. So my first connection now, I'm going to commit this transaction. This succeeds, and you can see that the change has indeed been committed to the database. So that's the basic write conflict. The second example I want to show you is an example with a deadlock versus validation failure. So I'm now going to use repeatable read isolation to generate a deadlock situation. So I'm going to read from row 1 with transaction A. This takes a log on row 1, calls repeatable read. Nobody is allowed to touch it. Then transaction B is going to read row 2, and then transaction A is going to attempt to update row 2, which will block, wait for the log on row 2 to be released, and then I'm going to attempt to update row 1, which is going to wait for a log for row 1 to be released. So this is a classical deadlock situation. So let me go ahead and take the log on row 1, the log on row 2. Now I'm going to attempt to update row 2 with transaction A. And as you can see, I'm now blocked, waiting for the log on row 2 to be released. With transaction B, I'm going to attempt to update row 1. This again now blocked, waiting for the log on row 1 to be released. And now the SQL Server Deadlock Manager detects that there is a deadlock in the system, and you can see that my second transaction was chosen as a victim, as a deadlock victim. Now let's see what happens when we use repeatable read isolation with memory optimized tables. So again, going to transaction A, read row 1, transaction B, read row 2. Now remember, there are no logs, so I'm not taking any logs. I'm just going to remember that I read this particular row, so if I want to commit, this row had better not be updated. So now I'm going to update this row 2. This update statement succeeded. I'm going to update this row 1 here. Again, the update statement succeeded because there's no logging, no logs. Now I'm going to attempt to update to commit my transaction A, and this in fact succeeds. Right? I did remember that I read row 1, and this row 1 should not be updated when I commit. And in fact, if I look for it, it has not been updated. Well, this update statement has been run in the second transaction, but it has not yet been committed. So my database has not changed. So this was fine. And now I'm going to attempt to commit my transaction B. And this in fact failed, because now I have my row 2. I was remembering, hey, this should not be updated. But in fact, this transaction A updated row 2 and committed successfully, which means that row 2 changed in the database. So now I can no longer commit. And we see here, in fact, a repeatable read validation failure error. And then I want to quickly show you what happens in a deadlock situation with read committed. So I'm now going to use read committed isolation with locking. And in order to get the same type of deadlock, I'm going to do first the update and then the select. So I'm going to first update row 1 with transaction A, update row 2 with transaction B, and then select row 2 with transaction A, and then select row 1 with transaction B. And now we have this deadlock, and again you will see that one of the transactions was picked as a deadlock victim. But with snapshot isolation, what we have is we update this row 1, update this row 2, but I just created new versions. The old versions are still available for me to read, so I can read my row 2 and then commit successfully. and transaction B can read row 1 and also commit successfully. So so if you just have a basic snapshot, you will also not get this same kind of failures where you would otherwise get a deadlock. Okay, so that is a transactions demo. So when wrapping up here, I want to call out some of the limitations that we do have in SQL Server 2014 for memory optimized tables and natively compiled stored procedures. So first on tables, we have no triggers, no database or server triggers or DML insert, update, delete triggers for memory optimized tables. In terms of data types, we don't have the lob types, so varchar max or var binary max are not supported, and also no exotic types like XML or CLR. In terms of constraints, we do support default constraints, but we don't have foreign key or check constraints. And we actually have, we document some of the workarounds for some of these limitations. I have some references for those later in the deck. Then we also don't support any schema changes, so no alter table. If you want to add or remove a column, you need to drop and recreate the table. Similarly for indexes, because the index data structure are very tightly coupled to the actual table row data structure. So to add or remove an index, you will also need to drop and recreate the table. And for natively compiled stored procedures, these are the main limitations for queries, so no outer join, distinct, or subqueries or case. So what we do basically support is the basic insert, update, delete, and select, also with joins and with and in the where clause, and we also support group by aggregation. And there are also limitations that we have in the built-in functions. We do have some core functions that we do support, but not all the built-in functions. So these limitations might seem a bit severe. Two things I want to comment on this is that, yeah, with natively compiled stored procedures specifically, you might need to do a bit of work to work around these limitations, but the performance gains are often worth it. The second is that we are working hard to remove many of these limitations for future releases of SQL Server. So we are still actively investing in this feature, removing these limitations. So to briefly recap, so we have these new memory optimized tables and indexes. They're natively compiled on create. So we have this DLL, which is used for the actual data access, for cracking the rows, retrieving column values, doing the matching, etc. We have this new type of index, the hash index. And you can also use a non-clustered index, which works a lot more like the non-clustered index you're used to for disk-based tables. There's just some consideration for choosing the one versus the other, where we usually recommend non-clustered as the safe baseline when you migrate your application, and you then later want to optimize your application by migrating some of those to hash. Then in terms of accessing memory optimized tables, we have the new natively compiled stored procedures, where we compile T-SQL stored procedures to native code, to DLLs. They provide the best performance, but have some limitations in terms of the T-SQL you can use inside. And then for interpreted T-SQL access, this is your basic T-SQL ad hoc batches, stored procedures, views, TVFs, any kind of SQL module. There you have virtually the full T-SQL service area. You can also do joins with disk-based tables, but not as performant as natively compiled stored procedures. For transaction semantics, two key things to keep in mind. So it's multi-versions, and isolation is snapshot-based. So you have multiple versions in the system, so that when you write to a row, anyone else can still read the older versions of the row. And the other thing to keep in mind is it's optimistic, so we don't have any locking, so there can be conflicts between transactions trying to access, to update, write to the same set of rows, so you need to take care of that in your app in the form of retry logic. So I have here a number of references. I assume this deck will be made available to you, so you can look up some more detail on the topics I covered today. And with that, I thank you. I'm not sure if we have time for Q&A, since we are already running a little bit late, I think.
Right, yeah, we do appreciate all your time. Unfortunately, we do have some questions, which hopefully maybe we can circle back and get back to the participants. I know we are out of time, but we would like to thank Microsoft and JAWS for doing a wonderful event. So we will see about getting these questions that we do have on the queue, and hopefully we can maybe just answer them back maybe on our website at appdev. It is appdev.sqlpass.org. Again, thanks again to JAWS and Microsoft, and thank you very much for everybody.
Yep.
All right, thank you, JAWS.
Okay, yeah, thank you.
All right, you guys have a good day or evening. Thank you.